it's an important part. And yeah, Dr. Simon will tell you in a minute, yeah, just how important it is for his business. Okay, yeah. So CT, like I said, most of you are aware of what it does. It takes a bunch of X-ray images, a bunch of different projections, and then it puts it all together, it reconstructs it, and then we have tools to visualize it. So you have different techniques to look at your part. You can do it rotational. There's many ways to do it. But the science is basic. You take a bunch of projections, X-ray projections, you put it all together, and you see what's inside. And that's what it is. So we have a bunch of 2D images, if you think of slicing through your part, and you can then reconstruct it. You can see relationships between the internal features, and then you can not just visualize it, but then you can measure things inside it. And you can do this automatically. So one good example that we have is, in this market, is a company who makes additive manufactured dental, I don't know what they're called. Instead of braces, you use this. You use these to gradually correct your teeth over time. And we take, you take a CT of the impressions, and then they, on the cloud, they come up with a solution, a treatment schedule. Then they print them all out and send them out. We do a full CT in less than 30 seconds. So you're getting this information very quickly. And yeah, it's really impressive technology. I'm looking around at some of the things that people are making, and I think, wow, that's neat. And I think if I ever need one of, well, hopefully not this thing, but I imagine I might need a knee thing or a shoulder thing. But to know that it was made for me and it was made perfectly would be a great thing for me to know. Let's say it that way. And we do all sorts of relationship-based information, wall thicknesses, porosities, measurements, and you can compare it to a CAD/CAM model. And I show you on this screen where you can actually see the difference between what it should have been and what it is. You can, like it says, get insights on the effect of defects. So if something isn't the same, you can simulate what it'll do, if it will have consequence. And you can also figure out, if you're mass producing, you can figure out how to fix your process for future parts. And that's where we turn over. We make the stuff, but the most important is to test it. So
thanks,
Dr. Simon.
So I am from IFW. We are a research institute. We are private and independent, and we are dealing with joining processes. And additive manufacturing are really, in my opinion, joining processes. So for us, we have a huge variety of processes. We concentrate on the material, and the main claim is what happens with or in the material when energy is applied. And this makes independent of the process. If it's a laser process for joining or for additive manufacturing or for structuring, it's always the same what happens in the material. Besides R&D, we provide also job shopping, and we are known, for example, for heat treatment of titanium parts made in additive manufacturing. We have seen a lot of individual implants running through our furnaces, or, for example, also for CT scanning. We have done a lot in the development processes for companies. Shipment or delivery is no problem anymore in Germany. UPS or others, express delivery, in the morning, 9 o'clock, you get the parts, and 2 hours later, a taxi driver can pick it up and bring it to the clinic. So in additive manufacturing, we have several processes: sheet lamination for diffusion bonders, DED for metals, 3 different processes. We have material extrusion of metals, and also for powder bed fusion machines. And this I will talk about. We start in the process chain with the characterization of the materials. We had materials in our system starting kilogram price of €5. These were powders for firework, copper powders we had in the materials for testing. On the other end, it's a 5-digit euro sum for 1 kilogram for aerospace application, for example. After we have built the parts, we can do the heat treatment in-house. We have a certified material testing lab, so everything can be done in-house. And at the bottom, you can see different images, what we have done in this additive manufacturing area. At the very beginning, 10 years ago, sometimes job shop have only built the outer shell of parts and not molten the core. And sometimes it was not easy to detect this because the measuring of the weight, it was every time the same. So we have started with X-ray, and then you can see different densities of powder and parts. Also, what you have seen in the video before, you can measure the difference in geometry between design and really manufactured part. But what is more important, you can look inside. You can see geometrical errors, or you can see cracks, voids inside. And for this, we have started 10 years ago with CT X-ray. We have 2 systems. And the most important things, if you want to stay ahead, you do not buy a system and keep it. You have to invest every few years. On the right side, this is on the older system. There's a third X-ray tube in it to get deeper in the material, to get higher resolution, to get the pores in a smaller range. So you have to keep and invest on this to stay ahead also in additive manufacturing. So I want to talk about a public funded project, the project Jahn. I'm an engineer, so don't blame me for not right use of medical terms. So we talk about spare parts. So if you have accident or cancer in the jaw area, it's very hard to get an implant, especially if it's especially designed for one. You cannot build 10, test 9, and the 10th is implanted. That's too much. So we had this project, and the challenges we addressed were regarding the design and manufacturing, and also estimation or prediction of lifetime. You do not want to replace it after 3 years, get another bracket inside because it's broken. And this was the main topic of the project. It was done by the University Clinical Hospital of Jena, 3DI. This is a provider of implants, and we are as building and testing facility. So typically in traditional machining of implants is done, and on the left side you can see a block and then the resulting implant, and over 90% of the block is going to chips. So, and titanium is not easy to machine, so it's time consuming. And to get a better solution, you can use powder and build the part. But you need some design rules, what can be done with the material. So the first thing was to have a FEA analysis about load bearing. If you have a jaw, you have high bending loads, and this was done in a model, and also to predict service life, to verify the model. Mechanical testing was done, dynamic and static at IFW, as well as biological testing for validation. So out of this result a model to calculate for each patient a special implant, also with regarding to the lifetime, and then also on a patient-specific jaw implant, all was validated. On the slide, you can see on the left side the build platform, and there you can see on one side, more on the right side, samples built in different orientation for standard fatigue testing. On the left side, you can see, for example, 2 sample implants, and also with the orientation of the implants, you can influence the stresses and distortion in the part. Like it is shown here, if you build it horizontal, it can build it very fast, but it's a worst case regarding distortion and also with stresses. For the standard testing, 3 different processes were used: machining by milling. Then you can see the samples X-rayed or CT'd on the right side, from the milled, from the EBM, electron beam melting, and for the laser beam melting process. And if you take a close look, I hope you can see it, we have also tested it with a real surface. We do not have machined the part because in most cases you cannot machine all areas if you implant this part, and then we use the same surface. There are typically other approaches to have a polished sample and test it and then add safety factors. But in our opinion, due to the young age of additive manufacturing, you cannot really determine the safety factors, and that's why we test with a real surface, and then we have the real, we have data about the real, what happens. Then you can see here on the left side another orientation which is better with regard to stresses and distortion. And you can see also the different supports. You can also play with this and influence with this the geometrical precision. For example, you can see where the holes are. There's red in the CT scan in the comparison between design and real manufactured part. And this is also due to the different setups of the supports. So you have also keep this in consideration if you build metal parts, especially for titanium, how to orientate the part inside the machine. But we are also known for fatigue testing close to the application, because we do not have really safety factors regarding if you have pores inside or surface roughness. So we typically design for additive manufacturing test benches due to the close to the real application. On the top, in the middle, you can see a test bench for the artificial bone material we used to apply the implant. And we have to know first what is the performance of the artificial bone material. Then we have cut it in parts and have applied the implant. On the left side, you can see a universal usable fixture for this. So we can have the highest load in the area of the implant, and if it's in the back or in the front of the jar, you can adjust the area of load application. Then you can see from the setup of additive manufacturing, then the green one is a comparison between geometry after building and design, and then before mounting the part on the artificial bone material. And on the right, you can see one of the setups. In this video, you can see the test in real. So from setup, measuring between the geometrical differences between design and then the real testing. And depending on the industry need, here it was set to 4 to 5 million cycles. And then we get the data. The rating of the data was done then by the clinic as well as by the manufacturer 3DI. So we were providing the data and the rating in the end, and the model to set up is used then by the implant provider for his layout for the implants for each patient. To sum up our talk, we have 3 messages. So CT is mainly the one method to test parts with regard to internal geometries, voids, flaws, as well as cracks, imperfection, and that's why CT scan should used especially for patient implants if they are individual manufactured. If you have an artificial hip and this is manufactured in a few thousand per year, you can optimize the part. If you have to build only one, you cannot do the optimization every time. So then it's, in our opinion, necessary to check the parts or test the parts. And yeah, it is highly recommended to do the CT scan of additive manufactured part. Thank you for your attention.
Thank you to the two of you. There are some questions.
Yeah, I saw some here.
Yeah, Jason, you maybe already saw the first question. As the name of your company is Consult. So
right.
Are you rather a consulting company, or also a machinery manufacturer? What is the idea? What is the business model?
Right. So it's a combination. So it was founded by a guy who wrote a lot of software for Cypher. Let's put it that way. And we created a software company that we ended up building machines to fill a need. So we are a manufacturer and we are both. So.
Okay, integrated.
Yeah.
Do you consider to scan each part in the hospital before it is used?
So if it's built only one time and it's critical, it should be tested. And as mentioned before, there are several companies beside us to doing this even in a few hours. So yeah, if you're close located to a hospital, it can be done, but I think it's more important to be close to the supplier of the part who manufactures the part.
How exactly do the two organizations that you represent collaborate with each other?
So yeah, we are in R&D and we want to stay ahead with equipment, and we treat the manufacturer with our requirements, and in the end the things which were developed for us are then sold to everybody. So we treat the supplier to get better equipment.
How is the collaboration going from your perspective?
Yeah, so far so good. The next question actually plays into that. So they want to be at the edge of the technology. So if they want to use nano-focus X-ray tubes or very high-resolution detectors, this technology is changing rapidly. And as we integrate it into our solutions, it makes CT faster and less expensive, because that was the border, and that was a hurdle for many CT manufacturers or CT users. Was time and money. So.
Okay, yes. I mean, great question for the end. What have been the most important developments in the past 5 years regarding quality improvements? And now, even more interesting for us probably, what is next in terms of innovation that affect quality?
Yeah, I think it's speed.
Jason,
it's faster and more precision. You get more details. You can scan pores up to 1 micron if you have the right detector and the right X-ray source. So I think this is a future development and still running.
Yeah, at a reasonable price. I mean, because anybody can measure take a whole day to measure something. If you can do it in a minute or 10 minutes, it changes the game.
Okay, thank you very much. We are at the end. There are more questions, so there's possibility, I would say, in the lunch break or so to approach you to ask more questions. Thank you to the two of you.
Thank you.